So now we're going to talk about synchronization. Remember, we saw an example of synchronization when we looked at adding up the numbers, how processors have to synchronize with each other to make sure they're done before they do more work. The example we're going to look at here is from a bank. So you have 510 euros in your bank account, and you've done two things. You've ordered something online for 500 euros, and then you go to an ATM machine and you attempt to withdraw 200 euros. And we want to see how this works. So what happens when these run on different processors at the bank? That is, they run in parallel. So here's our bank. We have a balance of 510. We have one processor, and this processor is going to process your online order. It's going to go through, it's going to load the balance from the bank, it's going to check if the balance is more than 500. If it is, it's going to subtract 500 and put the balance back. The second processor is going to handle withdrawal. It's going to load the balance, it's going to see if the balance is more than 200. If it is, it's going to take away 200. Otherwise, it's going to fail. It's going to say you don't have enough money. So let's see what happens if they arrive one after another. And now we're looking at the bank's computer. So now this is the DRAM. This is the memory of the computer. We have one variable in it, balance, which has a value of 510. Here we have time. So time is going down on the axis here. And we're going to start off, and processor 1 is going to load the balance. So we take that balance, load it to processor 1. It's 510. Then it's going to check if the balance is greater than 500. While it's checking if the balance is greater than 500, the DRAM still has 510 in it because nothing's updated it. It decides it is greater than 500, subtracts 500 from it, and stores the new value back. Now the DRAM has 10. Now processor 1 is done, and we've handled the online order. Now the DRAM has 10 in it, and processor 2 goes to process your withdrawal of 200 euros. So it loads the balance, gets a balance of 10. It looks to see if it's greater than 200. It's not, so it's not going to update the balance, and instead it goes ahead and tells you you don't have enough money in your account. So this is what we expect to have happen. We expect that we spent 500 online, and so we should have our balance go down to 10, and then that the withdrawal of 200 should fail. Now let's see what happens if these two things are processed at the same time. So processor 1 is going to go through again. It's going to load the balance. It gets 510. It's going to check the balance is greater than 500. Now at this point the DRAM has 510 in it, but at this point the withdrawal starts processing also. So the withdrawal goes ahead and loads the balance, and the balance is 510 because this processor has not updated it yet. Now in the next cycle, the first processor stores balance minus 500, so it puts 10 into the DRAM, and the second processor checks if the balance is greater than 200. It finds it is, and the next cycle processor 1 is all done because it's updated the balance. The DRAM will still have 10, and the processor over here thinks the balance was 510 before, so it goes and subtracts 200 from it and stores the value back, and now stores 310 in the DRAM, and finishes. So this is not what we expect to have happen. We might be happy that this happened because we get more money in our account, but the bank won't be. We expect that if we withdraw 500 and 200, we should have to have 700 euros in our bank account for that to work, not that we end up with extra money in the end. So what was the problem here? Well, the problem was that processor 2 didn't wait for processor 1 to finish. So processor 2 here went ahead and started processing while processor 1 was in the middle of processing. If it had waited until after processor 1 had written its value back, we wouldn't have had the problem. So what was the problem? The problem was we had two programs running at the same time on different CPU cores access the same data. Processor 1 was updating the data but hadn't finished writing the results back, and processor 2 went and read the data. So the data processor 2 read was outdated because processor 1 hadn't finished yet. So here's another picture of that. We have processor 1, processor 2 in our data. Starts out at 510. Processor 1 reads the data, and then while processor 1 is doing its computation but isn't done yet, processor 2 went in and read the old data. Right now, the way the program works, processor 1 owns the data, but processor 2 has no way to know that it doesn't have the data. Then processor 1 wrote back its results while processor 2 was calculating, and finally processor 2 wrote back its results. So what we need to do here is processor 1 needs to lock access to the data. So we need some way for processor 1 to say, I'm using this data, nobody else can change it. And when processor 2 starts, it needs to check, is anyone using this data, so do I have to wait? And this is called a lock. So Could the bank synchronization error that we just saw happen in such a way that you end up with less money than you expect? And the answer is yes. If instead of those being withdrawals from your bank account, they were deposits, we could end up with a smaller deposit overwriting a bigger deposit. So this can happen both ways. How could having a lock help with this synchronization problem? Well, if we have a lock, it can make sure that a processor finishes the whole update before another one starts. So what we need to have is the first processor get the lock when it starts, and then the second processor needs to wait until it can get the lock before it continues. This will make sure that the first processor is all done updating before the second one starts.